But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. "80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys. Titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then, the upper plate of the press begins its descent. Slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure. Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing. China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on. The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later: catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s, when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals. Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources: Russia and South Africa. 70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive. 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1200 degrees. Iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not palladium yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery white with a slight steel tint. Palladium's softer than platinum, so you can roll it, forge it, draw it into wire. Palladium's melting point? 2,828 degrees Fahrenheit, lower than platinum. Density? About 0.43 pounds per cubic inch, lighter than platinum, but still a seriously heavy metal. Palladium doesn't tarnish in air, doesn't react with most acids, only dissolves in aqua regia and hot concentrated nitric acid, corrosion resistant. But here's the key property, catalytic activity. Palladium speeds up oxidation and reduction reactions. On its surface, gas molecules get adsorbed, activated, react with each other. That's exactly what makes palladium irreplaceable in automotive catalytic converters. The entire journey from ore to metal takes months and involves dozens of processing steps. How does a palladium car catalytic converter work? The device looks like a metal canister installed in the exhaust system right after the engine. Inside is a ceramic honeycomb structure, like an actual beehive. Thousands of channels in this structure. Total surface area, several square feet. The surface is coated with aluminum oxide, a thin porous layer that multiplies the area hundreds of times over. On top of that layer, palladium, platinum, and rhodium, total weight between 2 and 7 grams. Palladium and platinum oxidize carbon monoxide and hydrocarbons into carbon dioxide and water. Rhodium reduces nitrogen oxides back to nitrogen. Exhaust gases at temperatures between 750 and 1470 degrees Fahrenheit flow through the honeycomb. Reactions happen on the metal surfaces. What comes out? Almost pure nitrogen, carbon dioxide, and water vapor. Efficiency? Up to 98%. Without a catalytic converter, a car dumps dozens of grams of toxins into the atmosphere every mile. With one, fractions of a gram. A modern passenger car contains 3 to 5 grams of palladium. A truck or SUV, up to 7 grams. Here's the problem. Palladium reserves are limited and running out. There aren't many accessible deposits left. At current extraction rates, proven reserves will last 20 to 30 years. Prices are climbing. The shortage is getting worse. Automakers are hunting for alternatives to palladium. They're partially switching to platinum. It's also a catalyst, but more expensive and less effective for gasoline engines. For diesels, platinum works better. Recycling palladium from spent catalytic converters is ramping up. Old converters get collected, crushed, and the platinum group metals extracted. Recycling provides up to 30% of palladium supply. It helps, but it doesn't fully solve the problem. Demand keeps growing. Around 90 million cars roll off production lines worldwide every year. Electric vehicles don't use catalytic converters, but their share of the market is still small. Hybrids still need palladium. The palladium market's unstable. Prices swing from $2,000 to $3,000 per troy ounce. Palladium has become a strategic metal. The entire automotive industry and urban air quality depend on it. And just like that, journeying from ore a mile deep beneath the Siberian permafrost, through months of chemical operations and ultra-precise separation, palladium emerges into the world, platinum's younger brother, now the champion of clean air. A few grams of silvery metal, hidden inside every muffler, saving millions of lives annually. The rarest of elements, 30 times scarcer on Earth than gold, has become critically vital to modern civilization. It's the paradox of technological progress. The more we care about ecology, the more we depend on rare metals. Every time you start your car, remember, beneath the chassis works a palladium catalyst, transforming poisons into harmless gases. A metal worth $40,000 per kilogram makes city air breathable. From the asteroid palace to automotive catalysts, 220 years of history for a metal that found its calling in the fight for ecology. But reserves are dwindling, prices are climbing, and palladium's future looks uncertain. Perhaps in 20 years, humanity will discover a replacement, or learn to recycle more efficiently, or switch to electric vehicles. But for now, palladium remains the thin silvery thread connecting a billion automobiles to clean air, the metal without which megacities would suffocate, the hidden hero of the environmental revolution, tucked away in every muffler.
Without this metal, there'd be no electronics, no smartphone in your pocket, no computer on your desk, no satellite in orbit. Every second, millions of microchips are being soldered worldwide, and they all depend on tin. The metal that 5,000 years ago launched humanity into the Bronze Age today connects transistors and processors. The oldest metal of civilization became the foundation of the digital revolution. How do gray rocks from the jungles of Malaysia become the silvery metal that flows from your soldering iron? You'll learn why tin doesn't rust, how it changed the course of human history, and why modern industry would collapse without it. Watch until the end. The finale reveals what's behind every microchip in your phone. This is the story of a metal that survived millennia and remained irreplaceable.
Tin's story predates writing itself. Around 5,000 years ago, in the 3rd millennium BC, someone accidentally mixed copper with tin. The result? An alloy harder and stronger than both metals, bronze. It changed everything. The Bronze Age began, an entire civilizational era named after a tin alloy. Bronze swords, axes, armor were sharper and lasted longer than stone and copper. Armies with bronze weapons conquered continents. There was one problem. Tin was rare. Copper could be mined everywhere, but tin only in a few places on Earth. Cornwall in Britain, Bohemia in Central Europe, the mountains of Afghanistan. Expeditions traveled thousands of miles for tin. Phoenician traders sailed to Britain's foggy shores across the entire Mediterranean just for tin. The metal was valued more than gold. Whoever controlled tin deposits controlled military power. Civilizations rose and fell depending on access to this silvery metal.
In the Middle Ages, tin was used to make tableware, tin cups, plates, mugs. Tin doesn't rust and doesn't give food a metallic taste. Rich people ate from tin, poor people from wood or clay. Tin soldiers became a favorite toy for children in the 19th century. They were cast by the millions. But a strange danger lurked. At temperatures below -13 degrees Celsius, with tin, something miraculous happens. The silvery metal starts turning into gray powder. This is called tin pest. The crystalline structure reorganizes, the metal crumbles. During cold winters, tin buttons on soldiers' uniforms turn to dust. Tin pipes and church organs inside unheated cathedrals disintegrated. Napoleon lost his army in Russia, not just from the cold. Tin buttons on soldiers' uniforms crumbled, clothing fell apart. Tin past played its role in history. Modern tin is treated with additives that prevent this transformation, but pure tin in freezing temperatures still turns to powder. Where does tin come from today? Tin is a rare element. It makes up just 0.02% of Earth's crust. The primary tin mineral is cassiterite, tin oxide, dark brown or black crystals, incredibly heavy, density almost 7 grams per cubic centimeter, heavier than iron. The largest deposits are in Southeast Asia, Indonesia, Myanmar, Thailand, Malaysia.
They account for about 70% of global production. There are deposits in China, Peru, Bolivia, Australia. Tin is extracted two ways: open-pit mining in quarries or washing from placer deposits. Placers form when cassiterite gets weathered out of rock by rivers over centuries and accumulates in valleys. Heavy crystals settle to the bottom. Lighter rock gets carried away by the current. In Malaysia and Indonesia, entire islands are made of tin-bearing sands. That's where most of the world's tin comes from. Then begins the dramatic process of transforming dark stone into silvery metal. Tin mining from placer deposits uses giant dredges. Picture a floating factory, a steel ship with a massive pipe that descends to the bottom. At the end of the pipe, a cutter head with teeth rotates. It tears into the bottom sand, grinds it up. Powerful pumps suck up the mixture of sand and water, slurry, and lift it to the surface. The ship has washing equipment installed, a system of flumes, screens, and centrifuges. The slurry flows down inclined flumes lined with special mats. Light sand washes away with water, while heavy cassiterite crystals get trapped in the mat fibers. It's like gold mining, except instead of gold, it's tin. Periodically, the mats are removed and shaken out. You get a concentrate, dark sand containing up to 70% cassiterite. The rest is impurities from other minerals. This concentrate is re-washed on special tables, blown with air to separate light particles. The final concentrate contains about 75% tin oxide. It's dried and shipped to the smelting plant. At the plant, cassiterite is reduced to metallic tin. The concentrate is mixed with coke, carbon, and loaded into a reverberatory furnace. It's a massive furnace, the length of a bus, lined with refractory brick. Inside, temperatures reach 2,400 degrees Fahrenheit. Natural gas or fuel oil burns. Flames reflect off the furnace roof and heat the mixture from below. At this temperature, carbon strips oxygen from the tin oxide. Cassiterite is reduced to metal. Molten tin collects at the bottom of the furnace, a silvery pool glowing orange from the heat. Tin's melting point is just 450 degrees, one of the most easily melted metals. The molten metal is periodically tapped through a tap hole, an opening in the furnace's sidewall. Silvery metal flows into ladles, but this isn't pure tin yet. It contains impurities: iron, copper, lead, arsenic. Refining is needed, purification. The molten tin is heated to 750 degrees and blown with compressed air. Impurities oxidize and float to the surface, a slag. The slag is skimmed off, the blowing repeated, several times over. Pure tin gets poured into molds, creating ingots weighing about 66 pounds each. Silvery white, shiny. Tin is incredibly soft. You can scratch it with your fingernail. But it has this amazing property. It doesn't oxidize in air. More precisely, it forms this ultra-thin oxide film that protects the metal from further corrosion. That's why tin cookware lasted for centuries. Today, most tin doesn't go into cookware, it goes into electronics. 70% of global tin production is used for soldering. Solder is an alloy of tin with lead or silver. The melting point of solder is around 400 degrees Fahrenheit, low enough that it won't damage electronic components. When you're soldering a microchip to a circuit board, the solder melts, flows into the gaps, cools down, and forms a solid electrically conductive connection. Without tin, assembling electronics would be impossible. Every smartphone contains thousands of soldered connections. Every computer motherboard, tens of thousands, all held together by tin. Tin is also used for tinning, coating other metals with a thin layer of tin. Tin cans, they're actually steel, just coated with tin inside and out. A layer of tin just a few microns thick protects the steel from rust and prevents food from contacting iron. Making tin plate, that's the second largest use of tin. Tin alloys are used in bearings, babbitt metals, alloys of tin with copper and antimony. They're soft, lubricate well, handle heavy loads. Organotin compounds serve as stabilizers in PVC plastic production. Global tin production runs around 350,000 tons per year. That's tiny compared to steel or aluminum. But tin, it's a strategic metal. Without it, the electronics industry grinds to a halt. Tin prices hover around $25,000 per ton, 10 times more expensive than aluminum. Tin reserves are limited. Accessible deposits will last maybe 30 years at current extraction rates. That's why tin gets actively recycled, recovered from electronic scrap during disposal.
Here's something interesting. Tin is one of the few metals we actively recycle. Electronic waste recycling has become an entire industry. Old circuit boards from computers, smartphones, and TVs get collected and shipped to specialized facilities. There, the boards are shredded, treated with chemicals, or heated. The tin dissolves or melts out, then gets extracted and purified. From 1 ton of electronic waste, you can recover up to 22 pounds of tin. This is economically and environmentally profitable. First, it reduces the strain on natural deposits, which aren't that abundant anymore. Second, you don't need to spend energy on mining and processing ore. Tin recycling requires 10 times less energy than primary production. In developed countries, up to 30% of tin comes from recycled materials. Japan, which has no deposits of its own, recycles up to 50%.
And just like that, traveling from dark cassiterite crystals in tropical placer deposits through the hellish heat of furnaces at 1300 degrees and countless purification stages, tin emerges into the world, civilization's most ancient metal, now the backbone of modern electronics. A metal that 5,000 years ago gave humanity bronze and empires, and today connects billions of transistors and processors. This is the story of how a rare element survived millennia without losing its value. What's more, it became even more critical. Every time you power up your smartphone, computer, or any electronic device, remember, inside, thousands of tiny droplets of tin hold microchips together. Without this soft silvery metal, there'd be no internet, no satellites in space, no artificial intelligence. Tin, the silent hero of the technological revolution, the metal that bridges past and future. From bronze swords of antiquity to microprocessors of today. 5,000 years of service to humanity. And this isn't the end. It's the continuation of a metal story that never goes out of style.